Alrighty, this is going to be my exam rework for this exam one, mechanical design. So I'm going to be doing problem 7 and problem 6 here with all three parts of them. So starting out, we have problem 6 here where we're trying to see this part here and we're really trying to find the design fully adjusted limit. SE is what we're really looking for. So this problem has a non-rotating bending normal stress alternating between the 0 megapascals and the max stress, which is just given to us by the normal max. And we understand that it is a 25 millimeters. We know that it's got that many cycles and it has a reliability of 99.9. So the part will be machined as said, and it's out of the steel here. So with the equation for the endurance limit, we're going to use SE, and we're going to use this SE prime in all these Martin factors to determine what that value is. So going over here, we can see that originally I kind of started with that same kind of process here with those kind of Martin factors, and then I eventually got to the point where I was able to find this KA. So how you're supposed to find KA over here is you determine that you're going to use this equation here for finding that Martin factor for the actual type of machine it is, and you use this table here for that. And I can see that's a machine steel, and it's supposed to be 304 and the negative 0.217, and I got confused with the hot rolled, and that is why I chose that. So that is why I simply mistaken that, and the same values were all the same, and that is the only value that gave me that. So working through this problem, we can see that we're going to have the Ka. We're going to find the value for that by finding the A and the B and applying it to our ultimate strength, which we were able to determine from the table. So using the table A20, we're able to find that steel, the 1040, and then we're able to determine, hey, it's hot rolled, and that is our ultimate stress, and that's our yield. So using our ultimate, we can then use this relation for that SE prime, and we can see that it is definitely less than 1400 megapascals, and that's why we multiply it by 1/2 to get 260. So working through that to the size Martin factor, we can now see that KB is going to be this DE divided by 7.62, and that's how we get that there. So with our diameter of 25 millimeters, we know that we're going to be using this one at least, and using that, we plug in our DE, which is related to 0.37 of this D. So that's how we get our DE there, and we get 9.25. So we plug that in for that, and we get our 7.62 and our negative 1.07 from the table over there. And that is how we're able to determine what exactly our KB is, which was that 0.9795. And as you can see, that is where I went wrong. Actually, no, sorry. This one is what I got right. It was that one with the reading the tables wrong. Now, going on to KE, which is the reliability, we can use our reliability table at 99.9 to find it is 0.753. And plugging those values, that is how we get that value there. So going into problem B, for that same problem, we're trying to find the largest value of that max at that many cycles with a Martin or just a factor of safety of 1.5. Now, to do this, we're going to be needing to have this equation here for the alternating. We're going to be using the alternating stress in the midline and the ultimate stress, and then we're going to also have that factor of safety. To find the alternating, it's going to be max minus min, which gives us this relation hit here, keeping that value. Same thing with the mid, it's going to be plus this time, and that's how we get that value there. So to find the ultimate, we're going to be keeping that 520 from the givens, which are kind of knowns, which are kind of messed up now. So we are able to use this alternating relationship here for that specific value, which is that A n to the B. And doing that, we can find A and B, which are given to us by these relationships here, and get those values, plug them in, and then that is how you get that specific value. So where I went wrong on here is I used SE prime instead of SE, where I should have been using just the SE, not SE prime, for the A and the B relationships, and this F should have been that alternating, or yes. And going through, we were able to see that I rushed. Same thing, how I'm kind of rushing now. I know 10 minutes isn't that much time, but I really should have used this equation where the M contains that max stress variable. Instead of trying to solve it like I did here, we want to keep it in terms of just that max. So once I knew that, I was able to plug in that value there, and I was able to solve for it, and we get a value of 142. So part C, I did get this one right on that, so we won't really do that, but that is exactly how you do that. And it did not fail, or yield, sorry, it did not yield because it's greater than 1. So problem 7. Now this one was a little bit different. It was this kind of weird shape here, and we were given its combined loading with the bending axial and torsional. We were given a whole list of values, and we are trying to find the fully adjusted endurance limit again with those Martin factors and that SE prime. So the SE prime we find the same way because of this relationship is less than 1400 megapascals, and that's why I multiplied by half, get 300. The Ka size factor was given to us right there, so it was given to us by the knowns. And the KB, we choose the smallest this time since it is combined loading. So within that, we're going to be finding all those DEs after using those in the table to see exactly what it falls in between. And using the smallest, we're going to choose the smallest from the relationship. So we had one, and we had all of those. I know I'm circling a lot. I don't have a laser pointer. Okay, so that is what we do. And then after that, we use the smallest when we use the K, and then the C was just the 1. So we use the K, the A, the B, the C, and we plug those all in there, and that is how we get the SE of 205.39. This one, I did not choose the smallest one. I just kind of chose a random tallest one there, which I was not supposed to do, and that is not the right approach to do there. So ignoring the other ones due to them being a 1, I could have ignored that last C if I wanted to. Now, going into part B, I can see that we have an ultimate stress or a endurance limit of 250, and that's what we're going to be using from here on out, not the one I got before. So we're trying to find the fatigue stress concentration factor of the normal bending stress KF bend. And this equation here is what relates to that. So we get 1 plus Q times quantity KT minus 1. We write down all of our knowns for that weird little shape up there. And using that weird little shape, we're going to be using this table that is tabulated there. And that is the tabulated for KT. Now, where I went wrong on here is that table was confusing to me, and I incorrectly used KT value. I kind of used this relationship and not the table. I also forgot the square root of R over this value here, or the square root, sorry. And for the square root of R, or the square root of A, I was off by my math. My math was wrong somewhere in here, and it was somehow off by a factor of 100. And going through this process now, we can see that we're going to start with that. Q, kind of that model tree, like in Creo. So going through there, starting at Q, we can find the A, the R, which is the A is given to us by this kind of funky thing here, which gives us that value. The R is just square root of the radius, which is 2, and that's how we're able to get that. So KT is from the table, which I take the radius divided by the small diameter, and we take the big diameter divided by the small diameter to get 105.1, 101 to this curve here, and then we go across, and I estimate the value to be 1.72. So using those values, we're able to find that KF bend is 1.568. Now, it wants us to use KF bend of 1.25 for future calculations. So we compute the design. What we're looking for is to compute the design cycle to failure. So the factor of safety was NF of, get off of there, get off of it. So a factor of safety of 1.75, fatigue strength fraction, which was F, 0.85. So we're looking for the number of cycles to failure. So we're going to be using that equation there. So where I went wrong is I was using the right final equation, but yeah, these values down here were messed up. So going in, we can see that this A and the B value for that is given to us by those relationships. Once again, we get those values. We multiply F by the ultimate strength, which is the same thing with ultimate strength. It's going to be that 600 here, so that's why we get 0.85, and we get the 0.85 from, given to us there. So we use another relationship for that ult again, and we're able, or stress AR, and we're able to get 415.6 megapascals. And now we're going to need to find these values for the alternating and mid stress, which we're going to need to sum from these 6 equations, which 3 aren't written, but we're going to need to use those KF values and multiply them all. Same thing with the T torsionals, and we're going to get those values down here. So we sum those up into that square root equation, and that is where we get that value. So once we get these values and we get the square root, we're able to plug everything back in, and we get this equation down here. And we get an N of 7,245 cycles, and it will fail after, or yield or fail after that. So same deal, I did not sum these m values here. So I did not find them individually as I did down here, so there should be like